All right. Good morning. I'm a little bit late today. I was hoping to get on by 7 a.m., but it is 8 a.m. now. I slept through my alarm. I had set not by too much, but just by a little bit, and I decided I would just take a little bit more time to get ready this morning before I get into it. In terms of where I'm at in the course, I'm nearing the end of problem set 10. I had some technical difficulties, very frustrating yesterday. Definitely it sucks when you have difficulties that are unrelated to the project or thing that you're learning. But in this case, the live streaming software, the thing that I'm using right now to talk to you, that allows me to have multiple cameras, that allows me to show what I'm writing, and also you can see me, and you can also see the PDFs that I have on the screen that allows you to see all that at once were not working. I just had to use my note-taking camera, and that meant I had to print things off so you could see what I was working. Hi, Rasmus. And so it was a little bit challenging. I got to say, I was a bit frustrated yesterday, and I think that also affected my concentration. I ended a little early. I was hoping I'm going till 6 p.m., but I ended around 5:10 or something like that. And it was just also because I was making a lot of mistakes that were not really I don't know this. It was just that my thinking is too fuzzy. I'm not able to concentrate. Now, what I'll say is that it's okay to have moments or days when you're studying or learning something where you don't have as much motivation, or you're not able to concentrate as well, or you're just making silly mistakes. For me, I don't really subscribe to the kind of peak view that you need to be sort of crystal clear and totally sharp in your focus at all times to continue studying. I think you still make progress even when you're in those states. You still make progress even when you're a little tired, you're a little bit having some difficulty focusing, you're still making progress. So I like to focus on time at the desk, time at the chair. Now, the only way that I kind of really moderate that view is just that if you are losing sleep, I think that that's bad generally. So I have been keeping up with sleep, but if you are cutting sleep to study more, that's generally bad. I don't recommend that. Or if you are really you're changing what you're doing, so that instead of doing what you really should be doing to learn the kind of effective techniques that I try to recommend, you kind of switch to, oh, well, this is hard, so I'm just going to read my notes, or I'm just gonna watch things. So that's where I kind of differ a bit. And some people maybe are wondering, well, what do I mean by effective learning, or what is the difference between effective learning and ineffective learning, or these kinds of things? And I think there's sort of two levels of this. So one of them is just choosing the right category of things to do that will actually work for learning it. So for a class like this, which is math and has problems, and the thing that I need to be able to do is to work with these mathematical structures to solve problems, to notice things about them, to be able to derive things about them. The only way to really get good at that is through doing problem sets. So this is sort of the effective practice. There's some supplemental activities, some drills, some things you can work on that will assist in that, but that should be the foundation. And so when I'm talking about ultra learning, which maybe sounds like this kind of extreme or unapproachable concept, really what I'm talking about is doing that hard work versus what would be more pleasant, which is I could have just watched the lectures and called it a day, right? I didn't have to go and do all these problem sets, especially when you're doing self-education. And so that is a big part of it, is just doing the work of doing the thing that you need to do, and not just being, I'm tired, so I'm not going to actually work on the things that really matter. Now, there's some flexibility there, and so a lot of the effectiveness is just in picking the right broad category of things to work on. But I've also been doing a lot of other little things that you'll notice, both in terms of how to break down problems of not understanding something, which is happening quite a bit. But you'll see me kind of go between getting explanations and working on things. I've been using this sort of spiral metaphor, so sort of doing the material in multiple passes. That's good for spacing. That's good for having your exposure to information spaced out, so you're not just getting it all in one go, all in one go, all in one go. So I am going to have multiple passes, which is good for long-term retention. But also, it's good because sometimes you understand something at a superficial level and you want to deepen it, and you can always go deeper. So I could have spent, you know, a month just working on the stuff from like one class of just broadening and deepening and understanding all those things and getting deeper and deeper and deeper. Whereas because that's not possible, the spiral metaphor also ensures that, okay, well, you didn't dig really deep in one thing, but you barely scratched the surface here because you ran out of time. So that's been the other reason I've been doing it this way, is just because seeing the whole course. So I've seen it all in lectures now. I'm almost done the problem set. So now I've seen it all in doing problems. And now it's just going to be, okay, what is the most valuable things for me to deepen my understanding in the limited time that I have left? So I'm going to finish problem set 10 today. And then after that's done, I'm going to do a full analysis of all the problem sets, basically looking at what I wrote, what the answer was, and what was the reason I couldn't get the answer. So there's basically three things that it could be of the reasons why it could be that I didn't get them. One is that I couldn't get it because I'm missing a concept. So there was a concept that was applying. And sometimes these concepts are, it's kind of fuzzy to distinguish, especially in a math class like this, between a concept and a fact, because what is a fact is very often in mathematics something deep and true about it. So it's not quite obvious to say where the dividing line is in a class like this. But a concept would be something like, well, I just don't understand what we're trying to do with taking these eigenstates, or I just don't understand why, you know, energy eigenstates are stationary, or I just don't understand, like this would be a concept. Then it could be a factual problem. And I'm going to be more limiting in what I'm calling a fact here, because in a class like if I were taking a business class or a law class or languages or something, there's a lot more facts. I don't need to know why a certain word is pronounced the way it is and what's the complex history of that to be able to perform effectively in speaking situations. So I would call it a fact. It just sort of points down to, can you memorize this? Here in math, there's a lot less brute facts. There are some though. And I would say that the kinds of things that I would qualify as a fact are things like identities, so trigonomic identities, just making sure that I have certain relationships memorized. There's been a lot of times where things have hinged upon recall, and then it'll be like this formula. Oh, I've got a little cat coming to join me, hey? I'm cat sitting right now, so if my friend's cat makes an appearance in the video, then you'll know why. But there's been a lot of cases where I've been doing stuff, and this is the formula sheet that I'm going to have for the actual exam that I just printed off in advance, just so I could get familiar with what's on that versus what's not on it. And oh, hold on a sec, I'm just going to pull up the blinds here. So much noise. So there are some things that we're just sort of, you know, recall this. And if you don't remember that, or you don't remember that relationship, then you can't possibly solve the problem. So there is a certain amount of memorizing, or at least remembering through active recall. And then finally, I would say there are procedures or technical abilities that need to be mastered. So I like to think of this sort of tripartite division of concepts, facts, and procedures, or concepts, facts, and skills, that are how you break down a subject like this. So what I'm going to do is, after I'm done, is I'm going to go through and I'm going to kind of write down what all these things are. And if it's a concept, the best way to get better at it is through something like the Feynman technique of really kind of developing that intuition for it. If it is a fact, probably the best thing to do is to do some kind of space repetition system like Anki or that kind of thing. I'm not going to have time to do that, so I don't think I'm probably going to invest in flashcards, but I may sort of jot those down and then just sort of every morning kind of test myself in the amount of time I have left on some of those facts. And then finally, there are skills. And so skills would be things like, you know, they would be procedures. So things that would have multiple steps that would involve, okay, you know, can you work with this in different problems? So some of them have been like recognizing when you need to substitute variables. Some of them would be things like, knowing that you have to do this and this to solve this kind of problem. Dimensional analysis, that's a really good example of a skill, because I know what dimensional analysis is. If I was asked just sort of plainly what are the dimensions of various constants and things, I think I would be able to recall them at this point. But if I'm asked to sort of say, okay, here's just a random thing quickly, what are the dimensions of this statement? I might not be very fast with that. And so to be able to do that quickly and accurately is going to be important for the problems. So going through all three of those things, going through those facts, concepts, and skills, that's going to be sort of my deepening point. Now, the question is, how deep can I get? In this class, it has been challenging. I've been needing help on most of the problems, and the problem sets are just very difficult. Now, I have some feelings about why that might be the case. One, it could be just that my grounding, so my foundation going into this class, was not as strong as it should have been, which is probably the case. I didn't take one of the prerequisite classes, and the classes that I did do, I did 8 years ago in the MIT Challenge, and it wasn't as if I had been working with them, like I'd learned them, but I think that they were also some things that I was getting, like, to pass the exam, I wasn't getting easily 100% on them. So I think an MIT student who would be in this situation, who's a physics student, is probably taking a bunch of other classes that use all these same concepts. So the foundation is really solid. However, there's been a lot of stuff that's just been brought up in this class that I've been struggling with. And so it could also be because there's recitation, there's the idea that you're working on this with groups, that you're interacting with the teacher. So I think that there is also the possibility that my struggles with this problem set have come about also from the fact that I don't have access to all the resources an MIT student would. That wasn't a huge problem in the MIT Challenge, but as the difficulty goes up, a lack of resources makes it harder to learn the material. And so I don't feel too bad about the fact that I've needed a lot of help on the problem sets. I'm just going to have to make do with the fact that I didn't have enough other materials, and this has been sort of my main materials for getting feedback and getting practice. So I don't know how the final exam is going to go. I'm going to do my best to get as close to exam readiness as I can in the time period. I only have the one exam, which makes it a little unfortunate, because if I do it and I don't pass it, or I do it and I don't get the best grade, there's no second chances. I don't have another one that has solutions, so I can't measure myself for this class again, which is unfortunate. So I'd like to get as close as I can. If I feel like I'm really not ready, like if I feel like, oh, there's no way I'm going to pass it, I might save it. I might not finish the exam in this 1 month period, just because I'd like to end it on a pass. If I had multiple exams, I would just do one just to see how it goes. But if I feel like I'm not super confident, I might wait, just because I would like to, get that, okay, I'm good on this class before moving on to another one. But if it looks like I'm sort of, I'm doing okay, then I might just do it anyways. Worst case, I just go on to, let's say, trying 805 or 806. At some point later, without having that real confirmation that that I quote unquote passed this class. I'm using pass, but this is just sort of by the MIT Challenge standards, as opposed to someone actually taking the class, because of course I'm just using their free materials. So I got a couple questions in the comments, and I'll just address those, and then I'm going to move back to problem sets. So Rasmus is asking, I have another question. If you're able to do this project in a language you learned, like Chinese, how would you approach this differently? I'm not sure what you're asking, Rasmus. Are you asking about this project? Like if I were doing these questions in Chinese? Maybe you can clarify, and then I can try to answer that question. All right. So I'm going to jump over now to doing these problem sets. So I do have the printed ones, but I think I'm going to just put those away because I prefer doing it with the PDF here. It's a little bit easier for me. So let me take my notes over here. Okay, we've got this and this. I have a big desk, but it somehow seems to run out of space when I'm doing this live streaming. All right, now let's go over to, I want, one assignments. And then we've got problem set 10. Actually, I should open this in a new tab, just because I might want to look at the assignments again later. Let me just get this over here. All right. So I believe where I left off was this super long question. Where is it? Here, and I finished B, and I made the very foolish mistake of figuring out, why does this not work, this equation not work, when this is equal to plus or minus 1. And it wasn't because this is a singularly bad solution. This isn't a singularly bad solution, but just that this transmission, this root transmission amplitude, is going to vary between 0 and 1. Because it's going to vary between 0 and 1, there is going to be a place where this overall fraction is greater than 1, which of course has no, there's no inverse cosine to that. So I didn't see that, which is super obvious, and I think I was just maybe a little bit tired, but let's move forward. I don't have that much left to do on this problem set, so I'm nearing the end here. So let's just remind ourselves of what we're dealing with. We're dealing with a lattice of delta function barriers that have this, did we figure out what the, what their, is it V naught or something like that? Yeah, V naught. No. Does it say the, oh, no. This is just, these are not delta function potentials. This is just some kind of arbitrary but reasonable potential barrier. And then it's just periodic. Right, okay. So we don't actually know the closed form of the potential. And we have this lattice of identical such barriers. And we have located our energy eigenfunctions from Bloch's theorem that are periodic in L. And then there was some, they just gave us this QL, Q being, of course, related to this, this Q being the crystal momentum, as opposed to K, because K is assuming that we are in an actual momentum eigenstate of the particle, whereas here we're not in an actual eigenstate of the particle, because this is not actually necessarily a plane wave, or actually even at all a plane wave. If we remember from the things that we've got, like our top band is almost the free particle. It's a little bit different, but we also have like weird things like this, and and those are clearly not momentum eigenstates, but they're kind of energy eigenstates of this crystal potential. And they have kind of a weird crystal momentum. And so given we have some scattering information, meaning that we have the transmission and reflection probability as well as their relative phase, we can uniquely determine the entire problem of band gaps and all that kind of stuff. So we've done up to here. We showed that there are, in fact, band gaps, and that's because for B, the function looks kind of like this. So this is plus and minus 1, and we have some kind of like, I believe it's like this. So it is only allowed in this kind of region, and the regions do get bigger as they get spaced out. So I will, this is the only place that the electron, these are the only allowable energies, because outside of this, there's no solution to this formula. And the bands get further spaced apart, and they also get wider as they get to higher energies. And then the sort of like limit at the top is that it's just a free particle, so all energies are now allowed. But at the bottom of the well, they're more tightly constrained. And now we're on C. So C is asking, suppose the barriers in V are very weak. What does this imply about T, R, and psi? Show that in this limit, the energy gaps are very narrow, and the width of the gap is around KL minus psi is equal to n pi, given approximately by E gap. All right. Barriers in V are very weak. Well, if the barrier is very weak, do we have anything here for... I don't think we have it in this formula. I think I just have to... Is there... I'm just wondering whether they want it in some kind of particular way. Well, all right. If V of x is very weak, well, we know, for instance, that T is going to go to 1. Reflection is going to go to 0. So basically, the lower a barrier it is less that's going to get tripped on it. Where we have phase and psi. So what is our phase is also going to change. Is it going to go to? It's probably going to go to 0. I'm guessing. I would guess that it also goes to 0. The phase. This is a phase shift. Where's C? Show that in this limit, the energy gaps are very narrow, and the width of the gap around KL minus psi is equal to m pi is given approximately by. So Erasmus is asking how I would do this if it was not in my native language. Honestly, if I were doing this in Chinese, there's going to be some difficulties, but this is not, I would say, a very difficult project because of the language. If I were doing this in Chinese, I mean, I would have to look up some words, but I mean, the same way that you would have to do anything. I think the language is kind of separate from the mathematical difficulties. A class where language would be a bigger barrier is where your like linguistic knowledge is aided in the conceptual knowledge. So if you were doing something like law or history or something where the nuance of particular words actually impacts your ability to do this. Whereas this, there's going to be kind of your mathematical difficulties and your linguistic knowledge. And I mean, it would have made the lectures a little bit harder, but they do have transcripts, so you could just put them in and translate them. All right. So I have to show that at KL minus psi and pi, the E gap is approximately equal to root R. Well, so at KL minus psi is equal to m pi, then this cosine term, so cosine of KL minus psi So how would I define the width of this gap? I want to present this as some kind of closed form solution. So we want, when this whole expression, hold on a sec, when this whole expression it's going to equal 1 when we have when root t so this is going to be equal to 1 when root t is equal to cosine of KL minus this. Yeah, the key to learning something in another language is just to make sure you know all the terms. So just make sure when there's concepts that are introduced that you get them translated to English. I think honestly academic subjects are a lot easier to learn. Like scientific subjects are a lot easier to learn in other languages because there's a standardization amongst countries. Like if I'm learning physics in Chinese, it's going to be the same physics. Whereas if I were learning a subject that might have actually like a different way of being taught, like I was learning literature in Chinese versus English, that's actually going to be a different kind of subject. So the distance of this gap is going to be so basically it's where this is greater than 1, less than 1. So let's focus on the positive side. Basically, we've got our cosine here. And then this is equal to n pi. So we can just replace this with n pi. So it's going to be n pi minus this is our band gap, right? T squared plus, this is just t plus r is equal to 1. So let's put that in. 1 minus r is equal to and then also the same thing with plus e. Is there a small angles approximation for cosine? Let me just see if there is. I know there's one for sine because yeah. So cosine one minus theta squared for 2. And so our theta squared is going to be, let's just say 0. Let's just say minus. So plus epsilon, and we have minus 1 minus r. It's 1 minus epsilon divided by 2. All right. And our band gap is going to be equal to, so what's our 2 epsilon, right? So if the band gap is 2 epsilon, this is divided by 2, so we just change these two. So EG divided by 4 minus. All right, let's square this on this side. So 1 minus r is equal to and we will just get the same thing over here. Minus oh. Hello, cat. You joining me to study here? All right. Do I want to leave that unfactored? So no, I think I just take this. So we got 1 divided by a minus. You have minus equals And then this is also equal to, get the minus here, EG4 minus EG squared over 16. And so we can cancel these guys. And we'll bring this guy over here. So we're going to have eight. Okay. Okay, cat. Hey. There we go. All right. So this would be R is proportional to, because once we take the square root of this, is 2 root 2. So that's roughly right. Sketch EQ in this limit. So EQ in this limit is going to be like this, right? I'm going to have well, I think in the limit we can even just say that it'll just touch, right? Kind of like that. Okay, cat, it's time to get done. Hey. Come on. All right. Let's see what we got for a solution here. C, where's C? Oh, this is probably 6. Where's C? Meaning of it. Oh, we did this one already. So we're in 6. And I think we're in 7 right now. Taylor expansion. So they did Taylor conversion, small angles approximation. So theirs is better than mine. I think I've only got one term. So 2 cosine of n pi plus e sine n pi minus, what was just minus e squared over 2 cosine n pi plus dot. You're back. Can't keep you away. He's learned to jump up here now, and now I can't keep him off. Hey, am I going to have to put you in the room? Come on. Come down. Hey. There we go. That's a little better. Hey, just sit down. That'd be good. Okay. Yeah, why don't I get you your ottoman? You can sit here. This cat is being too friendly. Wants to sit right up here where I'm doing my studying. So, Taylor expand, and then we've got what? We've got is minus 1 to the n, 1 minus e squared over 2 plus dot over root t. We get 1 is equal to minus root t approximately equal to 1 minus epsilon squared over 2. And we have root t 1 over minus r. This is yeah, proportional to 1 over 2. So the 1's cancel, the minus cancels, 2 cancels, and we get well, I did not think of doing a Taylor expansion for this, and their math was more complicated than mine, but I kind of got the same result. I mean, not to the same degree, though, so I don't know whether that would have been okay. D, suppose the barriers are very strong. What does this imply about TR and psi? So if they're very strong, then we're getting, the graph is going to look like this. Something like that, right? Because these sine waves are like that. Just very, very sharp. That's our V naught. And what does this imply about T, R, and psi? Well, T is going to go to 0 because I don't know how to explain why transmission is going to go to 0, but well, let's look at the function again here. Basically, we have root T this becomes very small. How do I show what does the phi go to? What do we know about the phase shifts here? I know this from another problem set. The phase, I think the phase goes to is it pi or pi by 2? Well, what's going to happen? What's going to happen here? Let me open up. Which set problem set did we do the scattering? I think it was maybe this one. This is the harmonic. This is angular momentum. Angular momentum. Coulomb potential. No, this is multiple wells. No. No, scattering was maybe problems at 7. Unitary operators, quantum evolution. Oh, here we go. So r equals plus or minus negative I psi. Can I derive what's going to happen to the phase? Obviously, it's changing where these things are occurring. I'm not sure how to determine what's happening inside. My guess, I'm just going to put guess here because I don't really have any. I'm going to say guess goes to pi, but that would just be my guess. I guess not. Yeah. Pi? No. Okay, no, minus pi. No, it's not going to go to pi. It's going to go to some function of k, right? K pi? K pi, that would be my guess. All right, what do I know about this? So I want to find the E band. So the energy in the band is when we have cosine of n over 2 pi cosine n over 2 pi is equal to t. I guess we don't need to. We can just keep it underneath. So let's just Taylor, do what we did in this solution. Taylor expand it to cosine of n over 2 pi. Well, this is going to be plus or minus epsilon. So minus or plus epsilon sine n over 2 pi. So this is 0. Oh, not 2. T. So in this one here, this is going to be plus or minus 1, but they're going to be the opposites. When is it going to be plus? When is it going to be minus? So for plus E, this is going to be minus, and this is going to be slightly positive. This is going to be minus. So we have and this cancels as well. So this is equal to what? Minus E, square both sides. I have the squared there. I'm going to get the square of 1 minus. This is E, so minus E. I would have this equal to still getting those minuses. Oh my god. The cat came back. No. Here. Come. There you go. See? Nose in the camera. Did he adjust this off? Let's see. Oh boy. All right, let me go back. See? That's better. Huh? In the limit of strong barriers, you expect a low transmission, reflection equal to 1 pi by 2. Ugh. Okay. All right. I would say that I basically got that right. E. For Vx, a delta function bearer with G naught greater than 0, use previous results to show that this is a tricky one. Okay. So show cotangent of the transition amplitude equal to 2kl over G naught, and T is equal to cosine squared sine. So let's get our problem set 7. So let's see solution set 7, problem number 5. Hmm. So what did we have for the barrier? Yeah. What do we have here to get this answer? So we're just looking at this for the single barrier. So for the single barrier, how do we get the phase? Open this problem set again. So phi is going to be equal to Oh, M over 2 E. What was our energy here? What was our G naught? This was equal to what? What was G naught again? It's 6. Do I have it here on my formula sheet? Oh, what is it? I think it's like M L. Forms at 6. G naught. All over R naught. Right. Or H bar. This is this is for the finite square. Well, where is that delta potential? Oh, here we go. What is our G naught here? This is length times the voltage here. Oh, man, I'm just so stuffed up today. Get rid of one of the HMRs. 2E. What was our addition? Cotangent. Okay. So this is arctan. This is arctan, Jesus. I need a cotangent. And if I take the cotangent of this, it's just going to flip it all around. So I'm going to get cotangent of phi is going to be equal to this on the bottom. I'm going to have h bar root m l 2e. I don't know if we can do that k squared h bar squared jazz. And it's just like, let's just see, this is going to be h bar squared, k squared over 2m, right? So if I did substitute that in, what would that give me? No, I don't think I can use that. Oh, this is root. This, I'm forgetting a root. So this will cancel the mass, and it will cancel the h bar, and we should get k. So I have root 2. Oh, there's a 2 here too. So therefore it's 2 KL G naught. So that is what I had from this, but I'm not sure. I thought that this was only because we had energies equal to these. I thought this had to be an eigenstate for that to be true. I guess we're considering each component wave. This is EI. Let's put EI. I'll do double I. T is equal to co squared psi. So if we have, what was it? One B over. So we can just take cos squared of this. This is our cosine. So cos squared sine equal to squared. We can just get rid of this guy. And what was our t in this problem? T was equal to and we want to express this in terms of G naught. So G naught was what to J? Where's our G naught? H bar squares cancel, m's cancel. We need equal to 1 over 1 minus I G naught KL. So T is equal to this squared. So you can get that squared. And anyway, I can reorganize this. Oh, right, but it's, geez, I gotta do, yeah, there. So we have one complex conjugate, so this is plus. I just times it by G naught squared. So they should all cancel except for the 2. Two plus. Why do I have a factor of 2 here? I must have lost a factor of 2 somewhere. It's right here. Why do I have 2? It's not 2, actually, it's 4, right? Where have I lost the factor of 4? I feel like I almost have it. Why do I have a factor of 4 here? This is norm squared. where I picked up this factor of 4 here, but I don't understand how I got it. No. I did a mistake here. Where did I have? How did I get to this point? I had. Oh no. There's just a overall square root, so that's okay. See, this should be over 2KL, but I only have it over KL, and that's messing everything else up. So I'm taking this. There's no H bar here, but there's supposed to be an H bar. So I'm taking this, which I have here. Take the norm squared of that. I get this. Add this on the top of the bottom. These should all simplify, except for this is a 4 and it should be a 1. Let me look at this trig identity again. It's 1 plus. I mean, it's always frustrating when things are like so close and they're not exactly right, because it has to be basically this calculation. We just took the definition of the transmission amplitude. We substituted in for G naught. Did I do something there that was supposed to be R? G naught is equal to ML over. Like, is there supposed to be a 2 there? Like, this is supposed to be 2 ML naught. I must just be missing a factor 2 in the definition of this G naught. I can't see any other way that this is. All right, so I'm not going to check the answers just yet, just because these were just show, so that not feedback isn't required for this. And they're all part of one section of a question. So part 3, use this result in your result from part A to reproduce the result derived from the lecture for the periodic array of the delta function barriers. Cosine of QL is equal to cosine of KL plus G naught over 2KL sine KL. All right. Okay, let's start working with it then. So we have this cosine of KL minus psi. And we're going to get a cosine of QL, so let's go cosine of KL. Root T is root T, yeah. And we're trying to show, what are we trying to show? So this is staying the same on the left-hand side. And on the right-hand side, we want this to change. Well, what can I say about that? No. This cat won't leave me alone. All right. Well, root T is going to be cosine of this. So root T is going to be cosine of theta. So we can change this to cosine of QL is equal to cosine KL. Oh, what are you doing? Oh my God. This cat is going to wreck my chair. Well, no one told you to go up there. What you doing up there? Oh my God. All right. Cosine KL minus theta is equal to, this is going to be cosine of theta, at least for this potential barrier. And we want to get it in what form? This cosine KL G naught over 2 KL sine KL. All right, and let's use our identity down here of the A plus B. So this is the top thing is going to be sine of KL minus theta is going to be cosine KL cosine of minus theta minus sine KL sine minus theta. Sine's an odd function, so this just gives us sine theta. Sine is equal to minus sine. Cosine is an even function. That's right. Cosine is an even function, so this just gives us this. Sine is an odd function, so this just gives us an overall minus sine over cosine of theta. So we have here, this cancels and we get cosine. Oh my God. What are you doing? All right. Are you happy? Yeah, get down. Get down. Oh, this cat wants to sit right here by the camera. And you don't want to sit on the ottoman. You want to sit right there. All right. So this is going to be cosine KL. So this is going to cancel, and we're going to have plus sine KL. And then this is going to be sine over cosine. This is going to be 10. And so if we want cotangent I can just flip this around and get G naught over 2KL. Voila. That was not as hard as it was. Now let's look at the plot here. I don't want to plot this. Yeah, I'm going to just leave that part off. So you can see just the very, very fringes of this cat in my camera right now. All right. Let's just look at the solution. This is solutions. All right. Yeah, there's a 2 here. That must just be in the definition of G naught that there's a 2 there. Okay. Well, all right. Same thing. Yeah. Oh, they didn't graph this. All right, let's just go on then. F. Now, consider a lattice of attractive delta functions with G naught less than 0. Again, plot EQ for large and small magnitude of G naught. What has happened in a single bound state of the isolated attractive delta function? So for G naught less than 0, this becomes an overall minus. So I'll just call it, this would just be cosine now we want to consider what is it? Energy is less than 0 for our bound states. So what is that going to be? Negative K? No. So for E less than 0, we have over 2m so that's going to mean that we need to have for negative E, so E 2m E over h bar squared, it's minus equals K, so K squared, so K is going to be equal to I call this? I root 2m r squared L minus r squared L sine of, so I can just move the I up here, plus sign, and then this is just going to be I root what do we have? 2m e h bar squared L. Here, so we have cosine QL equal to where is this solvable? I think that's the right way to do it, right? Is that we've got some K is now where does this have solutions? So this would be e to the, so if we factor this into two parts, one minus this, e to the I is that right? I think I did this wrong. What did I want to do? I wanted to factor this off. A sine is equal to sine plus a minus 1 sine. Oh, I did it the other way around, yeah. That's not really helping me here. I've got this cat encroaching on my studying space. All right. Maybe that's this cat before a little bit. Now what do I have? Now, there we go. Just move this tape so that I have a sense of where the camera ends. Down a little bit here. That's not terribly helpful, is it? We have some imaginary k, and when is that imaginary k going to cancel? This is also imaginary. When are we going to have a real value of this? Now get out of there. I just moved it for you. Right? There you go. Yeah. Yeah, that's all right. There you go. You know, I just make some space for you. And now you want to go right where I'm studying. All right. I feel like I should be able to get this. I'm just stuck a little bit because we've got an imaginary wave number here corresponding to a negative energy. And the question is, when is this going to have real solutions? It's going to have a real solution when, because this I sine I. So we have cosine IKL plus G naught 2KL. Let's not carry all the E terms here. So this is only real at two values, at plus or minus 1. And pi. And what about this stuff here? We've got a pure sine wave. It's going to have two parts. So the minus sine IKL is always going to be purely imaginary. And then this other one here is always going to be real. I think that's right. Am I forgetting an overall minus sign? I don't think so. So when is this going to have solutions? Let's see if we can draw it out. So let's just simplify it here. I got cosine IKL plus I have two lines here. Maybe I should put it in the other direction. So this is going to be R Which one's which? Is this real and this is imaginary? I think. So we have cosine IKL. This will be our KL line. We have I sine IKL. But this is scaled to a factor of this. So we have so essentially we have a vector pointing real. So this is going to produce, it's not going to produce a band, I don't think. It has to produce a band. Let me get the band of this. Yeah, I don't know. Let's see. Let's see what it says. All right, last question. Since the energy is real, now we want K to be either real or purely imaginary. For either sign of G naught, the equation we need to solve is always this. K is imaginary, is more easy to define K equal to minus IK, and the above equation translates into. Oh, okay. So I think this is where I needed to. So we have cosine QL is equal to cosine KL plus G naught over 2KL sine KL, which we already knew. Now we have kappa is equal to minus IK. And then this becomes UL kappa plus G naught 2 kappa L sine H kappa L. No bound states. Oh no. So always exactly one band of bound states. So this is something that I've gotten on a number of questions, and when I do my full review, I think I'm going to bring up, because this translation between cosines and hyperbolic ones is related to this exponential imaginary flipping back and forth idea. So you have just exponentials here, which don't have any periodicity, versus the periodicity, and that relationship is making a big difference. So there's one more bonus question here. Okay. So there's one more bonus question. It's bonus, so I'm imagining it's going to be quite hard, but I want to work on it just because it's extra chance for feedback, extra practice. And then after, I'm going to go through and do my review. There are still some questions from the problem sets that I haven't finished yet. So I have not finished a couple questions that required watching a video, a couple questions when I hadn't installed Java on this computer. This is a new computer. I hadn't installed Java on it yet. So because I didn't have Java installed, I couldn't use some of the little applets. So I can go back and do some of those as well. But I'm just going to do that in my review, because I think what I'm going to do is do this overall concept review, identify which questions I think are good candidates for redoing, because they're something that, you know, I should be able to practice. There's a lot of questions I got wrong here, so I could probably do a lot of questions, but I think I'd like to focus on, well, you know what? I might not do that yet. What I might do is do the full concept review, identify questions I didn't do those again, and then I might go through the exam and then use that as a basis of looking at exams that don't have solutions to see what parallels there are in the exams with solutions, so I know which questions from the problem set are probably more important to have mastered. Because there's definitely some derivation problems on the problem set. There's no way I'm going to be able to do that in an exam. Whereas there's other problems which are probably of the right kind of calculating difficulty that's going to be on the exam. So let's look at question 8 here. Standing waves at band edges. So the appearance of gaps in the spectrum of energy eigenvalues is a striking feature of the periodic potential. As we have seen, the widths of these gaps decrease to zero as the strength of the barriers between wells vanishes. Thus, the state at the top of one band and the state at the bottom of the next band becomes degenerate as the potential is turned off. Conversely, then, the periodic potential must break a degeneracy among two free particle states, with one state becoming a higher energy than the other as the potential is turned on. In this problem, we'll explore this process by studying the states at the band edges. So consider a lattice of delta functions studied in the lectures. Okay. And focus on the states at the edges of the band with the crystal moment of QL equals M pi. So basically, let me just try to draw a little graph of what we're doing here. We have for energy, we have these sort of bands that are allowed, allowed and disallowed. Where's my top for this here? Yeah, here we go. Allowed and disallowed. Just going to put some tape here. I always forget where the camera is centered and where it's not, because I'm not usually looking at the live stream. And so I've been using a little bit of masking tape here just to position it. And unfortunately, I repositioned it because this cat right now won't leave my desk, and I'd rather not fight with him. So we've got our energy here. So we have different kind of allowed bands here of and I guess the idea is that as we go to very small potentials, these gaps. So when we go from 0 to turning it on, this gap is going to push up some of the energies and down some of the energies that are allowed here. So energy eigenstates that previously existed right at the band are going to have to get lifted or lowered into. So there was a degeneracy here that is now being broken. So one of the eigenstates is going to go up a little bit. The other one's going to go down a little bit. The states, the edges, the allowed bands have QL equals n pi. Well, that just follows from the formula here. So A equals n pi because cosine. This is the same thing before. I don't. Because when the v is, this is, yeah. That just follows from the what we've studied so far. Are you getting down? All right. All right. Wave function is not periodic. All right. So that's kind of what we explored from last time here. And then what do we have for B? Let's start thinking through the qualitative shape of the wave functions at the band edges QL equals n pi. If we could turn off the potential, we would find two degenerate free particle states, sine qx and cosine qx, both of which are periodic with 2n L over pi. Now imagine gradually turning on the potential. What does the delta function potential do to our two degenerate wave functions? Make a qualitative sketch of the resulting wave functions. Which of the two states becomes the top of a band, which becomes the bottom of a band? What can you say about the higher energy state in the limit G naught goes to infinity? So, we have two free particle states, sine qx. So I'm just going to I'll do this one in pencil first. My sines and cosines are always look a little too zigzaggy. All right. So one of these is going to shift up, and one of them is going to shift down. Which one and why? So when we have a very small delta potential, it's going to do with this phase. So these have the same energy. So we have cosine QL. Right, this is our relationship. I think we can also substitute this for cosine. So let's not do this. Let's call this. So when t is going to be, let's call it root t is going to be. So the transmission is very nearly 1. So this is going to be root of 1 minus epsilon. So epsilon's a small number. And then what happens here? So we have, when this is equal to 1, we have cosine QL is equal to cosine KL minus phi. So this is at this QL equals n pi. So when this gets turned on, cosine of n pi well, let's consider the let's consider this first. Forgot to turn off notifications here. N pi. So there's going to be 2 possibilities. One when we're here on. So when we're considering our thing here. This we're going to have one's here and one's here, and I think they're going to. It's going to switch which one depending on whether we're dealing with the top or the bottom. So cosine of n pi. So let's just say this is equal to 1 for right now. So that would be the, which solutions would that be? would be for n equals, that would be these solutions. That would be 1 is equal to this phi. We already derived that was equal to cosine. Where did we derive that? We derived that already. This is this phi is equal to KL G naught. So we're just turning G naught on just ever so slightly. Do I want to adjust that here? Yeah, let's figure out what's happening here. So we're turning G naught on just, so G naught is equal to we'll just call it epsilon is equal to 2mv naught over what is G naught? 2mv naught L. I'm forgetting what G naught is. MLW naught for H prime. This is just going up by the tiniest little bit. And then our so this is just E. We're just turning this on just ever so slightly. Is there a way I can do this qualitatively without looking at this here? Was periodic in L. So that's here. Here. These would be our delta functions. So when these go up, no, not, oops. What am I crazy as over here? It's not obvious to me which one's going to get shifted. So we imagine dialing this up. So let's imagine dialing this up. So that's going to be V is equal to H bar squared 2m G naught over L. And this is going to be epsilon equal to very small. So what happens to these wave functions? So particle at this edge is no longer having allowed energy. Cosine of QL equal to this cosine of KL minus This just tells us the relationship of where these solutions are allowed, right? This doesn't really tell us. So this is going to be basically one, so it's just a question of phase shift. How would we figure out which one gets adjusted? Let's try it with the boundary conditions again. So we're going to have one function which is like this. If I can draw it properly, and then the other function is going to look like this. Man, my signs are not good. All right. those are our two functions. And what will we do to separate the energies? Well, when this turns on, I'm just going to do it over 2 periods because this is too much. So this is going to be our cosine of QL. So our matching conditions, so this is 0, and now it has to have a slight change in the potential. But our sign so it just shifts this forward a little bit, doesn't it? Our sign, if it has to go up a little bit more, shifts this back a little bit. I can't just shift it back. It has to do something else. Oh, okay. So we can just use the fact that there's going to be these slope changes too. It's not just shifting it forward because the period has to change. So when this has a little bit of a tilt, this goes from being here to being like, let's say like that. And so because it has to be like this one gets pushed. The peak of this one is going to be just pushed slightly forward. Because this has to be like this as well. looks like it's again slightly forward. But it was already going to be like that, so it's going to be... So our delta function is going to be here, so this has to be even more curved. So because it has to be even more curved, this is getting stretched out, right? So our cosine is becoming lower band, and our sine becoming bottom of higher band. And this is for n pi is equal to 2 for ... Because this is going to squeeze it forward, so this is going to move the peak, shift it over here. But then now we've got the peak over here, so we need to shift even further because yeah, it's going to stretch this one out. Whereas the sine function, because this is at the maximum peak, to make this the delta function, we have to kind of get a slightly smaller wave function. And I believe if we have the opposite here, and I'm going to say it also at 1, 3, ... opposite. That would be my guess. All right, let's see if that's right. So this is not the right answer. What do we have here? What's the reason? The reason is because So the cosine becomes the upper barrier. Yeah, so if we imagine this as wells instead of as delta functions, just hypothetically, and we had there's no need to treat there, whereas if it were here, if it were like this is maximum decay, and this is no need for decay. Okay. All right, didn't get that right, but I think I understand why this is the case now. Okay. All right, let's go to the next question. C. Now let's check this picture. To begin, identify the boundary conditions which theta e, I'm assuming this is theta e prime, must satisfy at x equals 0. So we have theta e prime from the positive direction has to be equal to right? Is this not right? Yeah. So this is right. Now let's go over the next question. D. In the region 0 to L, the potential is constant, so it can be written as a solution to the free particle equation. A kind of sine x of theta over e. Ooh, so basically, I'm going to rewrite this in terms of these. So let's just plug it in. Here goes theta equal to Do I have to solve for this? So A over B is equal to 1 from this. And so we get minus divide everything by B, we get minus K cosine kx plus theta. Really? Let me see something here. So we have this is equal to 0. So we have G naught over L sine kx plus theta. No, what did I do wrong here? No, this has to be plus L. And this has to be plus L. Then we don't have AB equals to 1. Hmm. So we should have something like this. So this right now, I don't want to. So B over A equal to sine. Right. And we substitute that in here. Divide everything out by A, we get minus K sine KX plus theta. X plus theta over sine kx plus theta plus L sine kx theta plus L, which cancels. And we get is equal to G naught over L sine kx plus theta. These just cancel. And I'm left with 0, and then I can't derive the rest of the equation. don't know that that's right. Oh no, there's a minus sign here. This is equal to this. It's an odd function. So that becomes another minus sign here. No, it still doesn't cancel. So we write down there. Rewrite this. Minus 1 to n a sine k x plus l plus theta. And we have a sine kx plus theta. And so we have a sine and these need to be equal. How do they get this? Oh, because k is 0. So we have a sine theta is equal to a's cancel. We get sine theta is equal to sine kl plus theta. And our jump condition. Wow, okay. I did not get that. All right, let's go back over. See, this is E. Half of the solutions to these conditions are standing waves with KL equals n pi. D equals 0. Do the states appear at the top or bottom of their bands? So cosine of, let's do that. A equals 0 and A. What do we get? Well, we get cosine just 1. Cosine of n pi is going to be zero is equal to 0. And what about this one here? We have sine 0. I'm going to say that these appear at the top of the bands because that's where it's most nearly periodic. Top of each. Top of their band. F. Should the other half of the solution satisfy Oh, yikes. All right, I don't think I'm going to grind through these right now. I'm going to just look at this. Other half of the solution says pan KL over 2. Oh, it looks like my neighbor's having some construction done. Lovely. So what are the other ways that we can solve these? So let's plug in this information here. How do I make it? How do I get it over here? I have to rework this formula, I think, in terms of... Yeah, I have no idea. Let's just look at this here. All right. I kind of skipped over the last couple questions there. This was an optional problem set. Oh, we've got a lovely construction. Great. All right. I think this is probably a good time to take a little break because I've kind of finished using air quotes here because there's been a lot of things that have gotten skipped or I checked feedback pretty soon. So I don't want to make the claim that I did these problems as if I were to hand them in and get a decent grade. But I've gone through all the problem sets now. So I've seen all the questions. So I'm going to take a little break right now. And then I'm going to get back to, after lunch, I'm going to get back to going through all of this, figuring out what are all the concepts that I'm missing. And I'm going to try to be as atomic as possible about this. I mean, sometimes there's going to be areas where they used a particular fact, and I should probably be aware of a family of facts that relate to that. So for instance, if there's a trigonometric identity, I should be aware of it. Well, there's a bunch of these. This is not the only one. However, a lot of the concepts are themselves sort of unitary that, there's just that thing that you have to know. And so what I'm going to do is go through all of that and then kind of from that list sort of devise what would be the best way to get good at all of those weak points in the time I have remaining and which ones are more serious than others. So I might even make a little bit of a qualification of the things that I didn't get in the problem set, but that I feel like I have now because I have done problem sets in the intervening time. So there's some stuff that's gotten more practice. So I'm going to make a list of that. And then I do have Yeah, rest of today, Friday, 5 days, and then another 2 days. So if I kind of discount today for doing this and another day for doing kind of the exam, it gives a good 7 days of practice. So there's a lot that I can do in 7 days. 7 days I should be able to do, let's say do over this whole problem set thing again, but I should be able to do a considerable amount of work. And if I put in the effort, I should be able to get close to where I'd like to be for doing an exam on this. So I'm going to take a little break right now because this seems like a natural point to take a pause and get a little bit bite to eat, do a little bit of work, and then I'll be back a little bit later to keep working on these.